Hello, everyone, and welcome back to our latest online event here at the University of California, Merced. My name is Ricky Hill, your e-recruiter, and I am so excited to be here with you tonight. We have a fantastic event about to start. The topic that we have for you this evening, of course, it's part of the Become a Bobcat virtual series that some of you may have been familiar with and joined us even as recent as last night. Tonight's topic, however, is chemical engineering, materials science and engineering, and data science and analytics. So as you can tell by the title, we have so much in store for you this evening, and I can definitely tell you that all of our panelists and presenters, they are tremendously talented and so accomplished in their field, so you are definitely in for a very special treat tonight. Before we get started, I do want to mention a couple of things. The first one is the college tour. Now, I mentioned that a moment ago in our brief opening, but let me go ahead and touch on that again in case you missed it. The college tour is an Amazon Prime special series, and they focus on different university campuses. We have our very own 30-minute episode focused 100% on our campus here at UC Merced. So not only will you be able to get a glimpse into how beautiful our grounds are in case you haven't yet had an opportunity to take a campus tour, but the most exciting thing of all is that we will also be showcasing 10 of our current Bobcats. You will get to hear from them their firsthand account of all of their experiences at UC Merced, why they love joining our campus and becoming a part of our Bobcat family. You will also get to hear about academics and housing, sports, research opportunities, which of course is very important to us here at UC Merced. And also you'll get to hear a bit more about where we're located here in the heart of California. So we're really excited that we can offer this to you. There is a fun fact though, Amazon Prime has not debuted this episode yet. So we have a special link that we have put for you over into the chat area. You can take a look at that later on, sit back, get your popcorn, take a look at that episode. Like I said, it is 30 minutes and it is exclusive about UC Merced. You definitely do not want to miss out on that. One other quick thing, if you have joined us before, you know that I have my little spiel to just give you some information about how to change your audio settings down in the lower left corner of your screen. If at any point you would like to adjust the size of your screen or window, click on View Options in the upper portion of your window. And of course, we are fully staffed behind the scenes to get to all of your questions and answers tonight. So make sure that you do use that Q&A button on your screen, send in those questions, and we will get to those behind the scenes, but we will also be holding back a few minutes at the end of our event to get to some of those questions live. I think that about wraps it up for me. I am so excited to be here with you tonight with all the great panelists and presenters that we have. At this time, I would love to invite Professor Viney on screen, and he can go ahead and kick off this great night. Welcome.
Well, thank you very much for that kind and enthusiastic welcome and introduction. Welcome to all the people who've joined us from however far you've joined us from. I will be telling you about two of our engineering degree programs today. My name is Christopher Viney. I am a professor in the materials and chemical engineering programs. I've been here for nearly 21 years now, so one of the first 8 faculty that was hired into UC Merced when we started to build it. And so, when you have questions afterwards, I can tell you, if you want, a little bit about the history of the place as well. And hey, I've stayed here for 21 years. It must be great. It's a third of my life. It's much longer than I've lived anywhere else. So, first of all, then, a little bit about our new degree in chemical engineering. So the new degree is offered by faculty in, and it's a combined program now, chemical engineering and materials science and engineering, 2 majors, one in chemical engineering, which I'm describing now, and another one, which has been established for a while now, in materials science and engineering. We'll get to that in a few minutes. So what you see here is a list of our faculty in the program. Okay, this is the folks who would deliver the chemical engineering and, in fact, the materials engineering degrees. Now, those of you who look carefully at that list of names might notice something a little bit unusual. It's something we're very proud of. The number of women on the faculty is very unusual amongst engineering departments. And so something of the order of 3/4 of our faculty are women. We also have 4 continents represented in our faculty here, so there's a lot of geographical diversity as well, so we can tell you about what goes on in the world as well as what goes on in our discipline. So what is chemical engineering? chemical engineering, as the name implies, it's based on chemistry, but it's the chemistry of making and the engineering of making stuff. So everything that we use, right? Every device, every bit of technology that we use, you've got to make those devices and those technologies out of some kind of stuff. And the chemical engineer is somebody who will, start with one kind of stuff and then process it. They'll melt it and separate it and mix it and distill it and do some chemical reactions and produce other stuff that does useful things. And it's that process of converting stuff into other stuff, raw material into useful things, agricultural waste into useful things. That's what chemical engineers do. So students will look at, it says, operation and design of equipment in chemical plants, and as well as improving process production. So making processes more efficient, more energy efficient, more sustainable, more green. So some of the concepts that chemical engineering students learn are listed. So we learn about chemical reactors, and then the mathematics and the practical aspects of moving stuff around through these sorts of processes, how you control those processes so they don't blow up and so they don't release anything into the environment that you wouldn't want them to. How do you manage energy? How do you get heat in there? How do you take the excess heat out of there to prevent reactions from running away? And of course, you want to do all that for safety, for the safety of the people who are working in the plant, and for the safety of people who live around the plant and who live downstream from the plant and who breathe the air that the plant is actually maybe contributing some gases to. So, and then ultimately, how do you turn basically stuff A into stuff B, and in a controllable, sustainable, safe, economical, efficient way? So jobs, yes, huge diversity of jobs, and so obviously in making some chemicals, traditionally the oil industry has hired a lot of chemical engineers. Of course, we're trying to move away from fossil fuels for the sake of the planet. So there's overlap now with environmental engineering, certainly any number of safety-related jobs. You could go into management, where you're actually responsible for decision making in these sorts of factory environments. There's a bioengineering component to it, so particularly food processing and agricultural product processing, materials in general processing, and wherever materials are used. So automotive, energy, electronics, semiconductors, consulting, so you pick up some wisdom and some experience, and you can charge people lots of money to share that wisdom and that experience. Law school. So law school, people who actually, they do very well financially, where they take a technical degree, and then they apply that technical knowledge in the context of how the law works. And people get things wrong, and so there are lawsuits, and somebody who's got the technical expertise as well as the legal expertise, those would be that's where the law school overlap would happen. And medical school. All kinds of engineers can actually go to medical school. You probably need to have enough biological background somewhere, but there's opportunities within the degree programs I'm describing today to also pick up biological knowledge. So in terms, okay, do you get paid? Yes, very well, actually. So chemical engineers enjoy one of the highest starting salaries of all disciplines. And materials folks get paid very well as well, but maybe not right out the gate. Chemical engineers start high already. And so August 27, 2003, average starting salary in California is starting salary. It's almost a six-figure number. And we'll get there pretty soon, I'm sure. So this is probably a little bit more detail than you want at this point, but for lower division requirements, lower division, that's your first 2 years, upper division is your third and fourth years. This is assuming you're being efficient and getting through everything in 4 years, which you can do. So you learn introductory ideas about chemical and materials engineering. They are linked, so there's a course that will introduce you to both of those. There's quite a lot of math. So yes, if you like math, then you certainly think about doing engineering of any engineering degree. There's obviously quite a bit of chemistry, and there's going to be some physics. So, a good, solid STEM background. Then there's a life sciences requirement. Remember on the earlier slide, I mentioned bioengineering, and so as a place where chemical engineers can go and work. So yes, there are some bio classes. And then some more sort of general engineering principles. Engineering 45 here, I can tell you a little bit about. That is Introduction to Materials. Engineering 57, that would be strength of materials. So there's going to be a strong materials component there. And all our engineers, not just in these programs, but all our engineers have to take a professional seminar. Now, how to be a professional? Because, of course, realize that engineers are not just somebody with a degree, but it's somebody who is professionally recognized. And that's why engineers, they tend to earn a little bit more than people in some other disciplines. It's in fact, there's a professional element, just like a doctor or like a lawyer. An engineering school is a professional school. All right, and then upper division. So about half of your units are going to be in upper division, more chemistry, more engineering, and then some very specialist courses, the ones that are in red, that would be particular to chemical engineering. And at the end of it, you do a capstone design project, and that is where you solve a problem that an industry typically would be interested in. So it's a real life experience. As you're about to get your recognition for being a professional engineer, well, you've got to work with professional engineers on a professional project. And that's capstone. Pulls it all together. You can demonstrate not just that you pass individual courses, but you can apply all that knowledge together as a sort of a holistic and synergistic whole. Right, and then some technical electives as well. So you can specialize in some areas that you may have particular interest in. So a minimum of 3 technical electives, and they're organized here to, they're consistent here with some areas that are of particular interest at UC Merced. And why are we interested? Because we believe that's where the jobs are, and that's where the future lies, and that's where the expertise will become valuable to local communities as well as to the country. So that we can specialize from chemical engineering, you can have a specialization in materials engineering, or nanotechnology, or environmental engineering. So, and I notice I'm just counting on the slide. It says aligned with 1 of 4 areas. I only see 3 on the slides. I need to go and talk to somebody about what the 4th area might be. Okay, unit operations, that's a very central part of any chemical engineering degree. And so unit operations, a very practical lab course. It's a 6-unit course, 3 whole-day labs per week, but fortunately, this would be run during the summer, so you wouldn't have a whole bunch of other courses distracting you from these intense days in the lab. But that's ultimately what can really determine the employability of a good engineer. It is what level of practical lab experience they've had. And here's a big one. Okay, lists the sort of things that people might work on. Right, so what sort of degree programs are we offering? The basic Bachelor of Science in Chemical Engineering, chemical engineering with a nano emphasis, chemical engineering with a materials science and engineering emphasis, or with a materials science and engineering minor, or chemical and materials as a dual degree. So it's like doing a double major, essentially. And we are looking to introduce, as we come up to speed on this degree, emphases in semiconductors and also in computational matters. And I was in a faculty meeting earlier today where we were discussing how to bring artificial intelligence and what will be the future role of AI in guiding the development of new methodologies and new products and processes in chemical engineering. So, fast moving, very much at the frontier. And I think when you pick a university degree, you should always think not just what is the piece of paper that I carry out from this, but what is the longevity of that piece of paper? And so what we're very conscious of is that when we teach, we want you to learn skills and practical, well, again, skills, I guess, is probably the right word, knowledge and understanding applications that will last you, for a professional lifetime. Okay, well, that's chemical engineering. Here's some description of the courses. I'm going to just gloss over those because it's a lot to read and a lot to remember, and it won't matter if you don't remember it right now. Moving on quickly to materials science and engineering, so MSE, the other degree program that I am representing today. My own background is actually in materials science and engineering. So what is materials science and engineering? Okay, we've learned a little bit about what chemical engineering is, but what is material science and engineering? The sort of buzzword byline would be from atom to appliance. It's selecting the stuff that you need to go and make the device or the technology that you want. Chemical engineering is processing the stuff. Materials engineering is selecting the stuff. What do you use? What would we like to have that we could use? What could we do better? Those sort of questions. So we take fundamental principles, again, lots of physics, chemistry, and some biology, making stuff which behaves in ways that we need and want it to. So it's which atoms, which molecules, what does it cost, what processes might be available that the chemical engineers could be working on, how does our material interface with the environment, and we want to be as green and sustainable as possible. And how do we know we've got the right material? How do you measure the properties? Properties, strength, stiffness, opacity, magnetic behavior, electrical behavior, all the properties. We have to make sure that the material does what it is supposed to do. Okay? And so whatever it is that you want to have to make your life easier or more comfortable, that you would like to be able to buy if only it was there, someone's going to have to make it out of some stuff. And that's what the materials person can tell you about. It is about the kinds of stuff that we can make things out of. Okay, well, what are the building blocks? Here we see a periodic table. Okay, so nature gives us about 100 different kinds of building blocks. These are the chemical elements. And so, which ones do you use? How much of each? How do you combine them? That is what material science would be. Now, realize we probably can't use maybe 20 or 30 of these things even here. We couldn't even use because they're radioactive and dangerous. So we wouldn't typically use them in materials. But we might use them maybe in a material that could be used for radiation treatment in a medicinal context. So again, structurally, no, we probably don't use these radioactive materials, but for some applications, we need to be experts in them. A quick example here. So let's just take carbon. Okay, well, carbon's kind of important. We have a lot of organic molecules in our own bodies, but carbon comes in different forms. It's the same atoms, but how are the atoms joined into crystals? Diamond on the left, graphite on the right. And we don't have time today to talk about nanotubes or buckyballs or other forms of carbon. We're just looking at diamond and at graphite. Okay, and what can we do? Well, you can make artificial diamonds with enough temperature and enough pressure. That's what happens deep inside the earth. That's how diamonds are made. It's basically carbon and it's been squeezed and heated enough, so it actually goes and makes diamond. Or there are other processes we can do on the right-hand side where maybe starting with some sort of oil or coal tar or some sort of pitch, and do a process and you come up with all kinds of different graphite. Graphite for pencils and graphite that may be very porous and graphite that might be essentially just in the form of a two-dimensional material. So all kinds of different things you can make out of the same stuff, carbon, but it depends how you organize those atoms. It's the structure, the basic crystallographic structure that matters, as well as the actual ingredients, the type of atoms that are in them. And here's some pictures of different microstructures. So some artificial diamonds there on the left, I believe, and the flakiness of graphite there on the right. So this is using a scanning electron microscope, which helps whoever was making these materials to see whether they've made, well, the right kind of thing, and also the size of the crystals or the flakes. That can be important in terms of the properties. So what's in there? Carbon. How is it arranged into crystals? How big are the crystals and how are they arranged into the piece of material you're going to go and do something with? We have to worry about all those different length scales. So here is a quick summary, actually, of material science and engineering. It is structure is important and processing is important, getting it to do the thing it needs to do and perform in the long time. And also at the end of the day, then going and seeing whether we've actually got all those properties and structures and everything and finding ways to measure and characterize them. So it is very stimulating as a field. I've been in material science myself. That is what I got trained in. And if I had to start all over again, I would probably do the same thing because it's been an intellectually very rewarding field to be spending, well, the last 4 decades in. Right, so material science drives technological progress. It's no accident that we talk about Stone Age and Bronze Age and Iron Age and Steel Age, and then we had aluminum, and now we're using silicon and plastics and things. But all of these different ages depended on the technology to extract and process the materials, which allowed us then to make new technologies to extract and process even newer materials. So just really where civilization has got to and where it will go is intimately linked to materials. Again, chemistry is important. So here we have actually one of my colleagues, Professor Wong, uses chemistry to make flexible electronics. So wearable electronic devices, they can be integrated into your clothing and they can measure things like blood pressure and the pH of your perspiration and any number of diagnostics to monitor your health built in unobtrusively into flexible clothing, but they're electronic. So just imagine that, 10 years ago, 20 years ago, people would have said that's impossible. Well, we're doing it. Okay? And we often actually draw our inspiration from nature. So nature makes fantastic stuff. It's had a long time to figure out how to make fantastic stuff. And so, nature hasn't patented anything. So of course we go and study nature. You want good fibers, learn from spiders. You want good lubricants, learn from slugs. You want good sunscreen, learn from a hippopotamus. I've just described 3 of my research projects in those couple of last sentences there. So bioengineering, biocompatible materials, mechanical engineering, materials that can behave in strong and extreme environments. A high-performance jet engine is made from stuff that was developed by materials engineers. Making the optical computer. Computers, 10 years, 20 years from now, they're not even going to be using electronic circuits. They're going to be using light to process information in ways that we can only just begin to conceive now. Okay, well, are there jobs? Do people get paid? Yes and yes. So these are, they don't start in materials, typically don't start quite where the chemical engineers do, but they catch up. And overall, you see, you do well. You can be making $161,000 at, these are what, 2021 rates. So you can be doing as well as a medical doctor if you work hard. Jobs, plenty of them. Particularly, you'll notice the dark green shaded areas in the map here. They tend to be places that have aerospace industries, very big employers of material scientists, so aerospace, transportation, patent law, so states with large populations and or large aerospace concentrations, defense type industries, certainly mop up the materials folks very quickly. We import more talent into material science every year than we graduate as a country. There are jobs, plenty of them. Sometimes people say, well, there are more jobs in mechanical engineering or electrical engineering. And yes, there are. But there's a lot more people competing for those jobs. So the job per applicant, materials is a very kind of safe and very productive way to actually go job hunting, because there's not so much competition for those jobs. Okay, we've got happy students. So very, very quick look here at Anthony. He's from Bell, California, down in Southern California. And he graduated from our program 3 years ago now, went and worked for the Air Force, came back, did a master's, graduated last year, and he's back working with the Air Force at a higher level now and managing a group of researchers. And a quote from him here, just he was happy that we let him loose on the expensive equipment, and we were happy that he didn't break it. But there are opportunities, and UC Merced it has a fantastic reputation for getting our undergraduates into labs and giving them experience. And if you look at departing student surveys, our surveys consistently rank us as the best UC in terms of the fraction of our undergraduate students who get research experiences. Okay, so what's special about UC Merced? I hope I've told you a few things already, but in materials, we focus on, we're forward-looking. We're looking at innovation. What can we make that makes the quality of life better? Long-term relevance, nano, very important, will be important for a long time. Those research experiences I mentioned. We are accredited by ABET in the materials program. We will be accredited in chemical engineering, but you have to graduate your first students, then you get accredited, and then it's grandfathered back onto the people who were in the program before it got accredited. So we're going to look for ABET accreditation in chemical engineering. And we have a minor in materials science and engineering. So on the slide deck, the department head, Professor Leppert, She types faster than I do, and she knows more than I do. So we're putting her name on the slide here. And so if you have questions directly for the department, and she might lateral them to another faculty member. I've been talking really quickly to get through this material to leave time for the next panelist and to leave questions at the end of the whole process. So I'm going to hand this back to Ricky, and thank you for your attention. I haven't been able to look at attentive faces, but I see lots of things happening in the chat, and so that means people are engaged here. Thank you so much for coming, and I will stick around to try and answer some questions at the end if there are any for me.
Wonderful. Thank you so much, Professor Viney. What a fantastic bit of information that was about chemical engineering and materials science and engineering. All right, without further ado, let's go ahead and jump right into our next section. Welcome.
Hello, everybody. I'm Alex. I'm happy to be here and tell you about data science and analytics bachelor's of arts. So I'm a management and system science professor in the School of Engineering. And what I'm about to tell you about, I'm going to abbreviate as DSA in what follows. In short, we designed this new DSA major with the big data and the AI revolution, and in general, with the future in mind. So let me begin with this schematic, which emphasizes the degree to which we are swimming in data, all of us. One problem associated with looking to the future is how quickly the future becomes the present. One example of this is the data deluge, which is the topic of this visual and the forecast it generated more than 10 years ago. This graphic's simple construction, designed around 4 circles, employs principles of storytelling with data, which you likely are familiar with, as it has become a valuable skill set in the area of social media platforms and the like. Because when attention is limited, then a data picture is worth a million words. And so visualization was the skill sets that we teach. In particular, the progressive increase in circle size quantifies the massive growth of data produced by modern society and science. In particular, each circle represents the amount of data generated in the scientific data producers over time, as shown, in terms of how big their data file would be if it were measured in terabytes. So how big is a terabyte? Roughly speaking, a terabyte is the amount of memory that a modern laptop can store on its entire hard drive. So as you can see, in 2012, the largest data set was on the order of 15 present-day laptops. Yet nowadays, the largest data sets can easily exceed 22 billion laptops. And I'm willing to bet that other data sets encountered in social media and AI industries easily exceed that amount. So why is the data deluge happening? A, because we are able to now digitize and record every aspect of human life. And B, because in order to understand stuff and to accurately forecast stuff, you need a lot of data. In other words, data analytics is about predicting the future. So let me now give you an example of data analytics in industry. All companies use historical manufacturing and present performance data to predict what to do and how to most efficiently do what comes next. Yet this role of predictive analytics is quickly expanding. For example, this is a screenshot from Tesla's presentation where they highlight data analytics as a primary component of their company's operating system. In addition to managing operations across their global hardware and software and service company, Tesla uses video data collected from over 6 million vehicles now to develop and train an AI model that will allow their cars to drive by themselves. Hence, this company uses data analytics to collect data, to integrate data, and to extract value and insights from that data, and then convert those insights into strategic action, whether that's to optimize their business model or to drive cars autonomously. So allow me to summarize what I'm about to tell you. The data science and analytics major develops a multidimensional skill set for generating data-driven insights that can inform real-world decision-making. This process from start to finish, I can describe using the following analogy. So let's start with something you're all probably familiar with, which is filling up the gas, your car with gas. But there's a huge pipeline of the petroleum refinement that takes that oil extracted from the earth and refines it and distributes it to your gas station around the corner. After all, they do say data is the new oil. So in this regard, let's think about the data refinement pipeline. We are all producers of data. So we can all think of ourselves in this first initial stage. Every time you send an email, take a photo with your cell phone, post a photo to social media, or make a purchase with a credit card, you are contributing to the data deluge, but also generating value in some segment of the data analytics pipeline. And so we're all now familiar with the infrastructure associated with data distribution and information distribution. We're also probably all familiar with the data refineries that add value to that data, whether it's the service platforms or the other types of corporations that use data. And of course, the data science and analytics jobs traditionally were in the areas of analysts and marketing, but now can span quite a number of industries. So this major will prepare you to be future leaders in a data-driven world. And along the way, you will become experts in the process by which information about our society and natural world can be codified into data, how to collect and integrate data by constructing a comprehensive representation of a system or a process, and how to construct a holistic analysis that provides new insights, transforming raw material into valuable insights. So now allow me to briefly explain the DSA toolkit, which incorporates a valuable blend of technical and soft people communication, teamwork, and management skills. So this is, so let me define DSA according to the only equation I'm going to present with you today. That is DSA equals data science times data analytics. So according to your high school algebra, you can probably see that we just factored out the data in the DSA. So in this simplified equation, data science refers to technical or hard skills, as they're called, whereas data analytics refers to soft or people-oriented or core skills, as they're called. So this major strategically combines these two, which distinguishes it from an applied mathematics or a computer science major. So data science refers to really the advances in statistical methods and computational algorithms. Data analytics considers the ways in which you use those data science methods to communicate with data, to design data services, design decision support tools that help people make decisions using the data, and the statistical inference for figuring out how cause leads to effect. And so we could actually replace that original equation with some actual kind of more descriptive words, which is computational methods and real-world decision support tools are the two pillars of the DSA major. So here's some of the things that you'll learn in each of those pillars. Again, statistics, data mining, and visualization techniques, machine learning, text analysis, and network science. And those core skills and methods will be then applied to problem solving in the real world and using teams and developing entrepreneurial mindset to translate those ideas to identify a potential market where you can make money. So DSA skill set is in high demand in a number of management-oriented professions. Traditionally, data analysts were found in the finance and banking sector, where frequent decisions involve big money. But nowadays, there's frequent decisions involving not just big money, but big implications in all sorts of management-oriented professions. And so increasingly, data analysts populate all corners of the digitized world, in particular at the intersection of management systems. So whether it's predicting people's behavior, which they do at grocery stores, whether it's predicting the markets and how to price certain products. This was the traditional business intelligence and information systems, but also increasingly in environmental systems where we can record the natural world and figure out how to best manage our valuable resources. So let me give you a quick overview of the program through this kind of progression across the 4 years. Starting in the first year, you're confronted with the foundations of data science and analytics. You're confronted with introductory programming and thinking like a programmer, using kind of the logic base of programming. But nevertheless, this is different than a computer science program because you're thinking about how to apply those concepts to the real world. The second year, you think about and learn about entrepreneurship, which is how to translate ideas into the marketplace. And so, as you can see, the progression quickly becomes now to, in the third year, to technical methods of data science and network science, and progressively leads you to machine learning, interactive data visualization, and a capstone where you'll work on a real-world project under real-world time constraints and other material constraints in your senior year in a team-oriented environment. And so through this coursework, you can elect one of 4 emphasis tracks: business analytics, behavior modeling analytics, policy analytics, or environmental and sustainability analytics, which will be featured on your diploma and kind of allows you to specialize. But nevertheless, this is a highly flexible cross-disciplinary program with only 17 required courses, which allows you to really, again, specialize in the corner of the world where you see yourself going. So how did we construct such a program, multidimensional major? Well, these 4 emphasis tracks are specifically aligned with the 4 different UC Merced departments shown here, which co-deliver the major. So the Management of Complex Systems department, the Cognitive and Information Sciences department, the Economics department, and the Political Science departments. As such, you can select from a number of courses in these areas that will allow you to excel in your particular direction. So thank you for your attention.
Thank you so much for that wonderful presentation yet again. We've had 3 wonderful presentations tonight and fantastic faculty on with us, as well as everyone who is behind the scenes. So we'd like to go ahead and start now our question and answer session. So if you haven't yet sent in your question, please feel free to go ahead and take full advantage of that Q&A button that is on your screen. Go ahead and send that in, and we will get to that now, as well as some of those behind the scenes. So the first question I'd like to go ahead and offer our panelists is, what engineering programs at UC Merced are ABET accredited? And is there a reason why a particular program maybe isn't or wouldn't pursue that accreditation?
Yes, so the accredited programs are environmental and civil, mechanical, materials science and engineering. And why do we go for ABET accreditation? Because there are benefits for ABET of having ABET accreditation in terms of applications to graduate schools and in terms of how sources of funds for programs. Why don't all the programs have ABET accreditation? It is perhaps more necessary in some programs than in others. So you could have an established program, something like bioengineering. They've been around for a while. They do not yet have ABET accreditation. And if you look around other universities, many of them don't. And so it's not sort of part of the culture in bioengineering. Now, if you look at something like electrical engineering, which was launched just within the last year or so, they are not yet ABET accredited, but they will be applying for ABET accreditation as soon as they've graduated. You have to have a graduating class. You have to graduate a student from your program in order to apply for the accreditation. And then what happens, there's a period of about a year where you fill in a lot of forms and you have to write up a whole sort of self-assessment report. Then the people from ABET come and visit and they assess us. And then when you get accreditation, your accreditation is grandfathered to people who have already gone through the program. So it's not like you sort of have to be a test case and the first people never get accredited. They will be accredited in due course. So I know that electrical want to do it. I'm sure chemical is going to do it. We've again discussed that today, actually, so chemical will do it. But it will be 4 years from now, 5 years from now, before it is actually physically accredited. I hope that answers some of your question.
Yes, that's perfect. Thank you so much, Professor Viney. And the next question has to do, is a little bit more general. Can we talk about our average class size and what type of level or typical engagement do you all have with the students? How much of a relationship do they get with you, kind of one-on-one and getting to know you?
Alex, do you want to go first on this? I have an answer, but I don't want to hog the microphone here.
Oh, no, please go ahead. I was actually typing an answer to another Q&A.
Oh, okay. And it's one of the advantages of still being a relatively small school. We get very close to our students in the best possible way. So I mentioned these research opportunities. So different professors offer different, maybe some have smaller groups than others, some have larger groups than others. But there is a sense, and certainly from the programs that I'm most directly involved with, and therefore I can speak, not just sort of making something up, but actually with knowledge, is that we celebrate the fact that our students continue to talk to us after they graduate. And it's not just because they want something, it's because they want to tell us how they're doing and how it is because of the relationship that they developed with their faculty while they were still here. And case in point, last night, I got an email from somebody who graduated about 3 years ago. No, it wasn't the gentleman it wasn't Anthony who you saw on my slide earlier. Another student who came from a background and from a family where there wasn't much university education. He was very much a first generation student. He overcome several obstacles during his time here, but we gave him the support and the mentoring to be able to do that. He's now working at Lawrence Livermore National Laboratory on some very high tech and really sort of nationally important projects. But he's now going back to graduate school at Davis. And he sent me an email saying, well, just basically saying thank you for that letter you wrote for me in December when I applied, because I got in, and of course I wrote right back and I said, well, this is absolutely fantastic. Now, go do great things there.
That's wonderful. Thank you so much for sharing that. And now we have another question here. If you can explain what a capstone is, what does that mean?
Alex, are you ready yet? I can.
Sure. So a capstone is a team-oriented project. And so typically, I believe most of the engineering majors in the fall of your senior year, you'll be assigned to a team of roughly 3 to 5 students. You're then paired with a real-world problem, oftentimes provided to you by an industry partner that UC Merced has established. And you work over the course of your final senior year to apply all the things that you've learned in your first 3 years and even that 4th year as you're continuing to develop real world skills, to see how problems are solved in the real world, which is slightly different than arriving to your final exam and that being your kind of landmark. And so the capstone is, again, to be short, the senior year project.
Very good. Thank you so much for that, Professor Peterson. The next question. Are prior computer language skills needed to major in DSA, and how should a person be confident, or how confident should a person be in programming to be successful?
That's an excellent question, and I think it partly addresses one of the other questions about how to distinguish this DSA major from the data science and computing major, which is more technical oriented. So actually, as we speak, the AI is learning to code it based upon commands. And so in the future, the ability to code is going to be relatively less valuable, and it's going to be more about how do you ask the right question. And so that's the best way that I could describe the difference. In this major, you're learning how to use the tools to then ask a question that's going to lead to to inform a real world decision, if that makes sense. So the coding level is less in our major and more oriented towards real world applications.
Very good. And another question. Let's see. Would someone be able to explain the difference between the DS and computing versus DS and analytics? I think we touched on that a little bit, but if we could kind of circle back to that.
So another way to think about this difference is think of a degree like chemical engineering versus chemistry. In the School of Natural Sciences, which also has the data science and computing major, you're thinking about the fundamental rules that a particular system must obey in order to understand the phenomena. In engineering, your mindset is a little bit different. You're trying to solve a real world problem by adapting to the constraints that you're faced with. So maybe you don't have a lot of money, so you have to develop a design that's kind of a little bit cheaper and could actually be made and sold, right? Or maybe maybe you develop a solution, but it's unsustainable. It requires a lot of poor management of scarce environmental resources. So that could be another constraint in the real world that you don't necessarily encounter when you're thinking about just how does this algorithm work and how can we make it better. So here we're trying to think about how can we apply these tools to develop new ways of improving our world.
Very good. Thank you so much for that. Another question. Can engineering students, can they study abroad?
Yes, in a nutshell. In fact, there is we actually sometimes get representation from the study abroad folks to the School of Engineering because they'd like to see more of our students engaged in that sort of activity.
Very good.
Hi,
Yes.
Ricky. My name is Pang Colvin, and I'm advisor for the School of Engineering at UC Merced. And I work with students who are interested in study abroad regularly. But for students who are interested in studying abroad, be sure to plan ahead so that this way you can potentially get course credit count toward your degree requirements.
Thank you so much for that extra information. That's very helpful. The next question, in order to become a data scientist, does someone need to obtain a master's degree?
You know, the future is what we're trying to predict, but it's nevertheless hard to predict. These days, I would say probably you specialize maybe and can. I think a lot of the master's programs in data science are with people who majored in some different area and want to kind of top off their skill set with something that's fresh and relevant, and that's the way in which they make the jump into that area. This is kind of more dedicated program across a 4-year educational plan. So that would be the best way to put it.
Very good. Thank you so much for that. And let's go ahead and move on to our next question. Do we offer any courses during the summer term that are related to any of the majors and minors that we talked about tonight?
In a nutshell, yes. And I know that we always offer a session in Introduction to Materials. There's always a summer option for that. There have been where the discussion now is how much of these courses would be online and when we would do them online versus in person. So you know, those rules and those opportunities can continue to evolve and change. But courses that are in high demand during the semester, several of them are available during the summer as well. And also because it's not just the engineering courses you have to do, but there are always general education courses and some more fundamental types of courses, and those often are available during the summer as well.
Very good. All right. Can we touch a bit on internships or research opportunities?
Alex, I'm trying not to hog in the microphone again.
Yeah, I'd actually defer that to you.
Uh-oh, okay. Yeah, so internships, it depends on the major, but certainly as we're building the chemical engineering program, we're building some very strong relationships with Gallo, and I don't know how far geographically spread our audience is, but Gallo is a major, let's say, chemical engineering firm. They make wine, right? That's chemical engineering too. Major firm not very far from UC Merced, 30 miles up the road in Modesto is where they're based. And so we're already planning the internships that will go with that degree. For material science and engineering, there are opportunities actually at other universities, in summers in particular, at national labs, at companies, and research. There's a certain amount of self-motivation needed in research. If you want to do research, talk to the faculty who are teaching any class that you take. So you're taking an introductory course in physics, or if that first engineering course you take, talk to those faculty. Go online, look at faculty websites. There are opportunities through, there are programs on the campus which match interested students with possible research opportunities. So make friends, join a sorority, join a fraternity, talk to your compatriots there, talk to people in the dorms or in the dining commons. Many different pathways. So it's sort of up to you. You want to do it. Send faculty emails, knock on doors. You won't be turned away. You might be channeled towards somebody who matches your research interests more than perhaps the first person you talk to. But you will find those opportunities.
Wonderful. Next question. Can a mechanical engineering major, are they able to minor in data science?
I believe the data science and computing major has a minor. The minor associated with our program is called management analytics and decision making. So it's not yeah, so that's the best way to put it. So there's a minor associated with our major as well as the other majors.
Very good. And then also, what is the difference between computer science and data science?
So I did address this in the question in A. Let me give it to you in terms of an inequality, in terms of the technicality. So that's how much you're diving into the details of optimizing the algorithms, designing the algorithms, improving the algorithms. Computer science is greater than data science and computing, which is greater than data science and analytics. So again, in data science and analytics, you're using and applying the algorithms to solve real world problems. So the best way to think about that is we all know how a cell phone works. We use it a lot, but we probably don't know actually how the internal circuitry actually works, right? So data science and analytics is about using the cell phone. Another major might be, the other majors are more about designing the internals of the cell phone.
Professor Viney, did you have something to add?
Yes, I just actually wanted, if I may, to return to the earlier question about research opportunities, something that I think sort of shows a level of dedication. We even managed to keep those going during the pandemic. And so we changed in many cases what the nature of the research opportunity was, but I can, again, most easily quote from the experiences that I directly had. We had a student who was using a portable microscope. The actual technology was developed by Stanford, but we were trying to do some microscopy. The student couldn't come into the lab. They went home to their parents in Southern California, and I sent them a kit to be able to continue the microscopy, and we actually got into the news doing that sort of work. So we really want our students to be able to engage in research, and a pandemic didn't stop us.
That's incredible. Thank you so much for sharing that. And actually, a little bit of a follow-up here for our final question tonight. Since the DSA major is new, will we eventually have some good research opportunities in that area as well?
Oh yes, that's really what the capstone project is. It's a research or applied design activity. Again, data oriented as opposed to, for example, chemistry oriented. That's probably the best way to put it. So it's a similar fourth year-long project that's kind of in consultation and directed by either industry or local kind of campus level management to kind of identify a real world problem and figure out some way to address it.
Very good. Thank you so much. And thank you both for your wonderful presentations tonight. At this point, I'd like to offer both of you an opportunity just to leave our audience with the last word tonight.
I'll go first. Don't be afraid to ask questions. Actually, as wherever you go and whatever major you're taking, you're paying for expert advice. Use the opportunity, go to the office hours, ask advising, ask the faculty, and learn and expand your horizon and move towards whatever excites you and engages you the most.
I couldn't put it any better. So please follow Christopher's advice.
Very good. Thank you both again so much, Professor Viney, Professor Peterson, all that wonderful information tonight. I know that this is one of my favorite events to help out on because I always learn so much. So thank you both so much for taking time out of your evening. And of course, a big thank you to all of our audience members for sending in all those questions. I do have a couple of quick announcements as we wrap up here related to admissions that I would definitely like to take this opportunity to share. One of them is that we are getting ready to go on the road with our admissions crew. So we do have a website for this. We'll hop that over into the chat box for you. We have 4 locations that we will be coming to, different areas and regions of California. One will be starting out on April the 7th in Los Angeles. We will next have one also in the South Valley in Visalia. We have one in the North Valley in the city of Modesto, and one over in the Bay Area in the city of Santa Clara. So what we hope that you can come to one of those, whatever city is closest to your region, and you can meet all of us there, or many of us there. You can learn more about other programs that we offer. We will have other student services available there for you as well. If you have financial aid questions, registrar questions, we will have tabling events that are there, and you will also get to hear from alumni speakers, among many other things. So please hop over to that website, pick your city, and get yourself registered. Of course, I have to mention Bobcat Day. That is Saturday, April 20th. That is the best day of the year, honestly. I know once I work that full day, my face hurts from smiling and meeting so many of you. And I'm always so excited personally because I'm always here on the laptop getting to talk to you virtually. I will get to be there to see all of you in person with over 5,000 other guests, other prospective and admitted students, community members, their families. So we hope that you can make it there. Part of that day will include similar things like what you're learning on these little webinars that are only an hour long. You'll actually get to meet faculty in person. You will get to sit through some other school presentations and get to ask questions just like you did here, but in person. You'll also get to meet other staff and students as well. Current Bobcats will be there. You will have the opportunity for campus tours, for self-guided housing tours. There will be over 200 tabling events with clubs and organizations, as well as many performances from other clubs and orgs, cheer teams, dance teams, things of that nature. As you can see, we're all so excited for Bobcat Day 2024. It is on Saturday, April the 20th, and we have dropped that link for you over into the chat box. Something else that is another important date for you to mark your calendar is the Statement of Intent to Register deadline of May 15th. So if your plan is to join the Bobcat family, please make sure that either by May 15th or sometime before, including Bobcat Day, we can help you with that in person. That is the deadline for the Statement of Intent to Register. And it's a very quick process, and that is how you commit to becoming a part of our wonderful campus here. One last thing I would like to mention is we do have a new YouTube series that will give you some insight into campus life. It is called Bobcat Life. We will drop that link for you over into the chat box as well, and you can take a look over there and see what else you can find. We do have other campus events in person. We have other virtual events coming up, so many to list, and I know we're running a few minutes behind, so let me go ahead and just encourage you to hop over to that admitted website for all of our events, and you can take a look and get yourself registered for everything. I'd love to see you here again. We hold about 2 to 3 webinars per week through about the middle of May. So I hope to see you again here, but definitely Bobcat Day, and submit that SIR by May 15th. It's been such a pleasure to be here with you. Again, my name is Ricky Hill, your one and only e-recruiter. Thank you so much for joining us. Have a great night, everyone.